So today I'm going to show you how to generate a structure file for a tile-based structure. So tile-based structures are constructed from natural tiles, and it's generally used for structures that you could build using cages. So for example, zeolites are probably the best example there. You can also use them for titanosilicates. So anything where they are generally constructed from cages and each atom within the cage is interchangeable. So zeolites, you can at a base level say that they are built of silicon, so silicon tetrahedra linked together by oxygen bridges. It doesn't matter if you move one silicon from one corner of the cage to the other corner of the cage, they're interchangeable. So that's the time when you want to use tiles approach. So it's actually a little bit simpler than calculating for net structures because you only need one file. You don't need this net interaction energy, you just need the structure file. But the calculation is slightly different, so I'll just go through this with an example here. So I've got a database here for zeolites, but let's try and do it from scratch with a CIF file from the IZA. So if I go to the IZA website, you should hopefully be familiar with this website, and I navigate to this LTA. This is zeolite A. I'm going to download a CIF file for it. So I'll just download it, and then I'll import it into my database. So now that I've imported this CIF file into my database, we can double click and see what the atom composition is. So if I go to this atoms tab, you can see it's got all the oxygens and species X because it can be a silicon or an aluminium, so they represent it with X. We don't actually need these oxygens, we ignore those, so we just look at the condensation between the actual silicon units. So we can delete those oxygens and we can convert this to silicon just for convention. So we'll just assume we're dealing with a purely silica zeolite A. So if I visualize this structure, you can see that we've got no bonding between these silicon atoms. So we need to calculate the bonding between these. We have to do the same thing that we do for molecular crystals. So we'll use AutoCN, but because we're only considering just valence bonds between silicon species, we can just use the solid angles approach. We don't have to think about hydrogen bonding. We can just use solid angles and we can have a strong minimum omega because we're looking for quite strong bonds. So minimum omega of 10 is probably quite good. And we'll press run. So you can see here that the silicon has a coordination number of 4, which you'd expect in a tetrahedral framework. If you have an interrupted zeolite framework, sometimes you have coordinations of 3 or 2. So those are represented by dashes if you go back onto the IZA. You've got these dashes show you that it's an interrupted framework. So these might have coordinations of 3 or 2. And the stars, they represent a disordered framework. That's not too much of an issue, but definitely look out for the dashes. So that's a good way to tell if you've actually calculated this correctly. So now that we've calculated our adjacency matrix, we can visualize the structure again to see that the bonds have been added. Now we need to calculate the natural tiling for this structure to generate the actual structure file. The way we do that is we use ADS, again, like we did for net crystals. But the options this time are going to be quite different. So the process for creating a structure file for a tile crystal is by calculating a tiling, not just simplifying the net. So we need to select a few different options here. So instead of saying save simplified net, we're going to have dimen calc selected. If you also want to visualize the shapes of your tiles in 3DT, you want to make sure you have this essential rings for 3DT selected here. Then we need to navigate to the topology window and set a few different options here again. So we want point symbols and all rings selected. You also want to have coordination sequence set to 1. And this thing here, max ring, this is quite crucial. So this will decide the largest ring size that it's considered when you're calculating your tiles. All the other options are just set as default. It doesn't actually use these bond types here. Then we'll navigate to tiling. And you can see, again, you need a few extra options selected here. So you want these dual nets, natural tiles, determine tile topology, which will give you the correct names of your tiles in your structure file, rather than just calling them tile number 1, number 2. Search for separate tiles, locally strong rings, and single tiling. You can see as you disable or enable these options, certain rules get enabled and disabled. So we want all 4 of those rules when we're calculating a natural tiling. There are cases where you might want to turn off rule B, but those are quite rare cases, and I'll cover them later in this video. So the other important thing on this page is this max tile size. So this will decide the number of vertices to consider when constructing a tile. So this largest tile here that can be calculated would have 200 vertices. This is quite a big overestimate here, especially for LTA, but it'll catch any tile. Then we can click OK and click Run. It's going to come up with a few questions here. So it's going to ask if we want to overwrite this .cgd file. This is what's read into 3dt. If you overwrite it, it will replace it with only the tiling that you're calculating right now. If you say no, it actually appends it to the end of the file. Same thing for the .tnt. Then you get to this page which says choose your central atoms, similar to what you did for the simplified net before. So silicon is going to be our central atom. If you add aluminium, you can pick that as well, but we've only got silicon. Or if you have multiple silicons, you want to select all of those. You can either right click and say select, or you can press insert on your keyboard, or you can press plus on your number pad to select everything. Press OK. You can just see it's running through the calculation. It also creates another child database, but this one will be called zeolite hash, rather than zeolite_c, which you would get with a simplified net. And you can see we've got LTA that's been calculated here. Now that we've calculated the tiling for LTA, we can visualize the structure again and see that the dual net has been added. So the dual net is the inverse of the tiling, so the center of each tile will have an atom placed at the center. So this one uses some dummy atoms here. So you can see you've got the main tile for LTA in the center. You've got these solder-like cages or tiles in the corners here that are going to form. And you've got these double 4 rings or T-cube tiles on these corners here. So you can grow the crystal and you can see those tiles. So now we need to generate the structure file for LTA after calculating the natural tiling. So for tile crystals, we don't actually need to generate this companion interaction energy file that we did with net crystals. We just need the actual structure. The energy for the tiles is input by the user at runtime. So we can actually just view the structure file by right-clicking and press View, or pressing F9 on the keyboard. And you can have a quick check to see if it looks like the correct format. This format is also covered in the manual. They do match between tile and net crystals, but the numbers can mean slightly different things. But the format's generally the same. So you can just press File, Save As, and choose a location to save the structure file. So I'll just save it on my desktop, call it LTA. So if I open that file, you can see it's the same as what was being displayed in Topos. So this file can now be used with Crystal Grower to grow an LTA crystal. After calculating a tiling, you can actually go back to Topos and view the tiles that you've generated. So if we go to Program up here and click ADS, that there will be the result of the last calculation that you ran. So if we scroll all the way up to the top here, you can see we've got LTA up there. So if we click Image, Primitive/Natural Tiles, that'll open an IsoCryst window where you can visualize each tile at a time. So it's got 2 tilings here, but let's just stick to the top one here, PPT1. PPT stands for Primitive Proper Tiling. And you can see that there's 3 tiles listed if we expand the window here, TGRC, TTOC, and TCUB. So that's the 3 tiles that make up zeolite A, or LTA. So you can see only one of them is bold at the moment, and that's this TGRC, which is the alpha cage, if you want to use cage nomenclature for zeolite A. So that bold one is the one that's displayed on the screen. So if we go back to the IsoCryst window and we just grow the structure a bit more, you can see the other ones become bold. That's just saying that the atoms that construct those cages are now actually grown in the crystal structure in IsoCryst. So if we select TCUB up here, press Hide All Atoms and press Apply, you can see it hides all the other atoms except for those that construct this TCUB, so you can see what shape that tile is. So if we repeat that process, grow the crystal again until all of them are bold, we can then select this TTOC, also called a sodalite cage if you're using the cage nomenclature. And you can see we've got this one tile here displayed on the screen. So if we repeat that again, display that TGRC again, we're back to what we had at the beginning. So it's a good way of seeing the atom arrangement in the tiles, if you want to just have a quick look at them. The other option is to use 3DT. So 3DT is really good software for making nice images for reports, which show these tiles with all their faces kind of shaded really nicely. And it can be downloaded from this website here, gavrog.org. But I'll cover how you use 3DT in a separate video. So I mentioned earlier that you can come across some slightly more complicated cases with zeolite frameworks. So you can have interrupted frameworks, you can have disordered frameworks, and you can also have frameworks where you don't want to calculate the natural tiling, you want to calculate a modified form of the natural tiling. So this means it follows some slightly different rules to the example that I showed here, but this approach will work for almost all of the zeolite frameworks known currently. So I'll just point you to two papers which are essential reading for natural tiling of crystal structures. The first paper is this one here. This is more of a general paper, so this talks about applying natural tilings to nets in general. So this is for all crystal structures. But remember, you only want to use tiles in the circumstances that I mentioned at the start of the video, when species are interchangeable. And this paper here is where you'll find all the general information about natural tiling. This will have all the rules for natural tiling. I'll cover that in more detail in the next video, but here's the reference here. And the second one, which is this natural tilings for zeolite type frameworks. So this is specifically for zeolite frameworks, and you've got the reference up here. But this talks about why natural tiling is better to use as a building unit for zeolite frameworks over the many other proposed examples. This one's more detailed and goes into more about zeolite frameworks. But I'll cover these with the more complicated zeolite frameworks in the next video.